indeed, and I'm going to present results that were mostly produced by Alessio Basti, who was here over summer for 3 months as a visiting student from Chieti. And it's very much also still work in progress, but I think it's still, I would really like to know what you think about this, so let's see. I guess we all agree that patterns of activation within an ROI contain more information than just reducing an ROI to a single voxel or an average. So that is the whole basis, the whole point of MBPA and RSA analysis. But yet, if it comes to connectivity between brain regions, we usually reduce activity in these regions to a single activation value, either per time point or per stimulus, depending on how you compute your connectivity values. Of course, there are there are already quite a few multivariate connectivity methods around, which I'm not going to explain in very much detail. But they all, produce basically a measure for the strength of connectivity between brain areas in different ways. So it's about linear dependency of multivariate time series between areas. What they don't provide, or at least what, to my knowledge, people haven't really looked at in much detail yet, is the actual transformation of the patterns from one brain area to the next. So the voxel by voxel mapping, ideally, between one ROI and another one. And that is what we try to address, at least with a few first steps here. So the idea that we had is, well, if you have your activity values in one region, let's say per stimulus, sort of stacked up as columns of a matrix here, and you do the same for another ROI, is there some sort of transformation? And in our case, we are looking at linear transformation. Is there a transformation that transforms every pattern here into a pattern in another ROI? And once we have this transformation, we can see if we can extract some more meaningful features from this transformation matrix. So at the end, we would like to see if we have different ROIs, how are different voxels from one ROI connected to voxels in another ROI. So how can we do this in a linear framework? So I mentioned, so we assume two ROIs, in this case n stimuli. If we stack the patterns that we get for these n stimuli into columns of our matrices x and y for two ROIs, then what we want is a transformation, so a matrix multiplication of the patterns in one ROI to the other ROI. What does that remind you of? So it's the general linear model or linear inverse problem. So we solve this in other areas of our analysis work. So it's basically a pseudo-inverse, or we can use Tikhonov regularization, ridge regression to find a solution. We have to add a lambda here, which causes a bit of trouble later. But this is basically how you solve this linear equation. So we can actually get, with these, in this framework that I've just presented, we can get an estimate at least for the transformation of patterns from one ROI to the next, to another one. And then we can also think about things to do with it. So for example, an obvious measure that we can derive from it is the goodness of fit metric, like the explain variance. So does a linear transformation actually explain any variance from one area to the next? We can look at sparsity. So is this transformation does it mostly consist of zero values? And finally, pattern deformation metrics. So how are the different dimensions of the input patterns sort of transformed into the output pattern here? So that means, are certain dimensions lost, amplified, dampened, what have you? So I'll explain that in a bit more detail in the following. So the idea of sparsity, I guess I don't have to motivate residual variance or goodness of fit. But I think sparsity, for example, can be related to topographic mappings. We know quite well that sensory cortices are topographically organized, for example, with respect to visual fields or motor, different effector types, for example. But some authors have also claimed or found that this is also true for non-primary sensory areas, for example, in parietal cortex. And then other authors have made a bigger story about that and have said it's a general principle of the cortex that topographical mappings are preserved also in brain connectivity. So there's the idea of a topographic connectome. And actually about 10 years ago, some authors tried to term the acronym UQTOMS, University Quantified One-to-One Mapping. I like mappings better actually, but mappings it is. I don't think it has really caught on. But maybe that's also because people haven't looked yet. And now with these transformations, if we can reliably estimate them, we might be able to actually look at these things in more detail. Estimating sparsity is a little bit complicated, so let's assume we do have a sparse transformation here, so a matrix mostly consisting of zeros and some ones here. I mean, if we have noise in our data, and because we are using Tikhonov regularization, which smoothes our estimate anyway, so we can't really expect to get exactly a sparse transformation like this back in our estimation process, even if the real transformation were sparse, so we will get something like this, maybe still some bigger values than others, but no value will be exactly zero. So we have to find a way of dealing with that, and especially in the presence of noise. And in the spirit of, this is a bit complicated, so I'm going over this quite quickly. I hopefully get the main message across here. So first of all, if we have different levels of sparsity that we can, for example, simulate, like 90% would be 10% non-zero values in our transformation, then we can decide, we have to find a threshold that we basically decide divides the zeros from the non-zeros. So at a certain threshold, everything above the threshold is counted as non-zero. And if we move that threshold along, if we make it bigger, then obviously fewer items will survive this threshold, or fewer elements in our transformation will be non-zero. So if we count them, we get what we call the density here, so the rate of density of the non-zero values. And this rate of decay here varies depending on the actual sparsity of the original transformation. So that means once we have this, the decay rate of this curve, we can fit an exponential here, and then one parameter describes the decay of this curve. We actually know, or we can estimate the actual sparsity of the original matrix. The problem is that these curves also change depending on the goodness of fit, or in other words, the noise levels in our data. So it's ambiguous with respect to actual sparsity and the noise level, so the goodness of fit of our linear transformation. So in brief, what Alessio did, he actually simulated lots of transformations with different levels of sparsity. He also simulated them in the presence of different levels of noise, and then you can actually plot the rate of decay estimated from the simulated data and plot them as a measure of goodness of fit and the actual rate of decay here. So if now you measure something in your real data and you find out, you have your goodness of fit and your rate of decay from your own data, and you see where your point lands in this two-dimensional image here, then you can reverse engineer, depending on how close it is to one of these curves, what kind of sparsity the transformation probably had in the first place. So takeaway message, by just running these simulations, we basically have something like a table from which we can pick, determine the sparsity of our transformation based on what we find in our data. The third metric that we defined was, we term pattern deformation. So it's well known that certain brain areas are very category selective. I mean, for example, inferior temporal cortex very highly selective to faces, but certain other types of objects as well, while early visual cortex is not. So the question then is that reflected in any way in the transformation between early visual cortex and inferior temporal cortex? Are certain patterns amplified or certain patterns dampened? So this is something we can detect in the eigenvalue, singular value spectrum of the transformation. If the transformation preserves all patterns of early visual cortex, it should have a very flat singular value spectrum here. So there's some decay here because there's some noise in these simulations. If, in the extreme case, the transformation would only project one pattern from early visual cortex to IT, for example, it should only have one singular value. So it would have a very steep decay. And again, we can estimate this decay, the parameter that describes this curve from our data. And unfortunately, it's also influenced by noise, so we have to take the noise into account. And just like the procedure for sparsity, we can simulate this for different simulated transformations. So in the end, we have something like a lookup table where we can check where does our measured value fall into this image, and we can then determine the parameter of our singular value decay curve here. Okay, we applied these three metrics to a data set that has been used quite a lot in previous literature, mostly by the Kriegers-Korte and Muir group. There are only 4 participants in there, unfortunately, so there's not really much statistics to talk about, but this is very much a proof of concept study in this case. We had 96 color photographs, including 24 phases and 8 places. and we had 4 RIs, early visual cortex, inferior temporal cortex, fusiform face area, and parahippocampal place area, and we are only looking at the transformations from early visual cortex to any of these 3 here. Oops. Let's start with some good news. Some information is actually preserved by our linear transformations. Of course, it's possible that the linear transformation doesn't explain any variance, and it's simply pointless to compute them. The brain is not linear. And we used, I should also say, I think I didn't mention that earlier, we used a cross-validation procedure to determine these linear transformations and regularization parameters. So we can be pretty sure that what's left here, I mean, the linear transformations that we do obtain in the end do actually represent some true features of our data rather than overfitting of these data. So here we look at the representation of similarity or dissimilarity matrices. This is the true one in the FFA with a very well-known, blue square here at the top left and faces in particular sticking out. And with the neural images eye, looking at it a little bit like that, you'll see that there's also something like a blue square here. And the estimated if we use the estimated transformation between EVC to IT, so this is basically the same representational similarity matrix computed after we've estimated the transformation, only used the patterns from EVC in order to compute what we predict in FFA, and then computed this matrix here. And well, the correlation between the two is moderate, 0.3, but you can clearly see some of these features in the similarity matrix are still there. So linear transformations at least capture some of the information that is contained in these patterns in these 2 RIs. If we look at the residual variance, first of all, if we look at all 96 stimuli, when we estimate this transformation for all 96 stimuli, from EVC to inferior temporal cortex, we get about 25%. It's not very high, but who has ever checked residual variances, in the general linear models and fMRI analysis? So I guess we should be happy with what we've got there. But the interesting thing is that if we look at the face stimuli and the place stimuli, I mean, there are very few of them. But interestingly, if we only look at face stimuli, the residual variance, I got this wrong, the explained variance. The explained variance in FFA goes up. And if we only look at the place stimuli, the residual variance in PPA goes up. So this is not significant, but this is. So at least the pattern of the direction of these effects is in the expected direction. So we see this dissociation between face and place stimuli in FFA and PPA in this measure. For sparsity, so these are basically these kind of 2D lookup tables that I mentioned earlier. So these are the values with respect to goodness of fit and the rate of decay that we estimated from our data. And depending on what shaded area it falls in, we can reverse engineer the level of sparsity the transformation probably had. And the interesting thing is the level of sparsity is quite high. So if it's actually here in these white areas, it's a level of sparsity above 90%. And this is the case for almost all of these transformations, for all stimuli here together. And the interesting thing is that the sparsity seems to be a bit, actually no. So here we show these results for the face stimuli in the top row, for ITC, FFA, PPA, and here for the place stimuli in the bottom row. And you can see that for the face stimuli, the sparsity is higher for the transformation from EVC to FFA, and for the place stimuli, it's higher for the transformation from EVC to PPA. Again, we see this double dissociation between face and place stimuli and FFA and PPA in this measure. Finally, pattern deformation. These results are less clear. I mean, it's at least the pattern of results for FFA and PPA here, so it's really difficult to talk about these differences here. But we can at least say that for all of these stimuli together, the rate of decay for the singular value spectrum is quite high, suggesting that this transformation is not a simple rotation of the input patterns. It doesn't preserve all the information from early visual cortex when it projects them into FFA, PPA, or ITC. So that is interesting in itself. I mean, this certainly needs to be investigated in a bit more detail, what exactly these patterns are that are or are not preserved. But in this case, we don't see this very clear or interpretable dissociation between FFA and PPA. Okay, after all this, I mean, we made first steps to compute the linear voxel by voxel transformations between patterns in different RIs and derived some novel connectivity metrics. So the goodness of fit, the sparsity, and the pattern deformation derived from these linear transformation matrices. Of course, the brain is nonlinear, but I think we've shown that linear methods can provide at least meaningful approximations. The first results with only 4 subjects look promising, but of course with 4 subjects they're not very reliable. So at this point we can only say it's a proof of concept, and hopefully we can apply these methods to further data sets in the future. These methods can, of course, also be applied to EEG, MEG, or ECOG data, and then also including time-frequency domains, which makes it possibly more exciting, but also a bit more complicated. Nonlinear extensions are possible, but then the question is how to interpret them. So you can, of course, let a neural network loose on these patterns and see if they predict, like Ancelotti did in a recent study. But then the question is, how do you interpret the actual transformations that you get out of it? So the nice thing about our matrices, the linear approaches, so you get matrices and you can really interpret them as voxel by voxel transformations between 2 areas. And finally, noise is a big problem, but I think that's the case, well, for everything basically, but for all connectivity metrics. So if you don't have a good signal in your RIs, then you can't really expect reliable connectivity, but I think we've made some good steps in the right direction there to deal with that. That's it. Thank you very much.